what we're looking at here is the tangent function. Several periods of the graph drawn. The asymptotes, which occur at odd multiples of pi over 2, are marked with dashed lines in red. Like all of the trig functions, this is a periodic function, which means it repeats itself on intervals of fixed width. So we have an interval from negative pi over 2 to positive pi over 2. That is a total width of pi. And then the same behavior repeated over and over again on intervals of the same width. Now, like with the sine function, we will examine the characteristics of the tangent function, including what the inputs and outputs represent, so that we can then have a better understanding for what the inverse tangent function is actually asking us. So, the tangent function, as with all trigonometric functions, takes as its input an angle in radians. Now, sine and cosine are the two easiest of the trig functions because their output values refer to some of the most obvious characteristics of the circle, an x and a y coordinate. Tangent, however, is still something that we can hold on to. The tangent of an angle is actually the slope of the terminal side of the angle. So, those things kept in mind. The domain of the tangent function is interesting. Most angles out there, most angles, have produce a terminal side that has a measurable slope. There's only a few that don't. Whenever the terminal side is vertical, meaning whenever the terminal side is coterminal with pi over 2, or coterminal with negative pi over 2. As I mentioned before, all of the odd multiples of pi. Odd multiples of pi over 2. Anytime the terminal side lands in one of those positions, the terminal side is vertical and the slope is undefined. If you prefer the interpretation of tangent as sine of x over cosine of x, at any of those places where the terminal side is vertical, cosine of x is 0, and you end up with a 0 in the denominator of sine over cosine. Now that makes the domain a little bit tricky to write if we're doing it in terms of intervals. Every now and then it's easier to write the domain rather than saying these are the input values that are included, we can turn around and say, well, these are the input values that are excluded, and that actually is easier to do here. The domain of the tangent function is that x can be anything except pi over 2. And, well, we could use I did mention coterminal angles, but we'd have to write two different families of x values here because the things that are coterminal to positive pi over 2 are not coterminal to negative pi over 2. Instead, though, they are still regularly spaced, and that's the idea of the coterminal angle formula, that all coterminal angles are evenly spaced from the previous one. So we ended up using multiples of 2 pi to represent a full turn of the circle. We don't need a full turn of the circle here. If we're at pi over 2 and we go halfway around the circle, we end up with, again, a vertical but downward terminal side. And from there, if we go half a circle again, we end up back at coterminal to pi over 2. So instead of n times 2 pi, we can do n times pi. So if we go to pi over 2 and then go every half turn of the circle in either direction afterward, we will always land in a position where the terminal side is vertical. Now, of course, that would be for the entirety of the function, which is not what we need here. We need something that is restricted. Fortunately, tangent kind of has an obvious restriction. Since each individual section is isolated from the others, all we have to do is pick one of them. And in keeping with the guidelines for restrictions, we should keep the one that includes x equals 0. So this central piece of it right here, that gives us a restriction of negative pi over 2 to positive pi over 2. Note that this interval, unlike the restriction on the sine function, this interval is open because the function is still undefined at negative pi over 2 and pi over 2. So we cannot actually include them. Now, the range of the function is, as the graph suggests, approaching the asymptote, we go towards negative infinity, and approaching the other asymptote, we go towards positive infinity. This should, I hope, make sense because the closer we get to pi over 2, the steeper the terminal side is positively sloped, but it gets steeper and steeper and steeper and steeper and steeper, approaching an infinitely steep slope, but positive. Exactly the opposite as we approach negative pi over 2, all of the terminal sides in quadrant 4 are negatively sloped, and they get steeper and steeper and steeper as we go towards that vertical position. So, moving over to the inverse tangent, which is the goal of all of this. Like with what we did for sine, the inverse tangent can be defined by taking what we know of tangent and interchanging the roles of input and output. So if the inputs for the tangent function were angles and radians, then the outputs of the inverse tangent function are angles and radians. Now, like I explained in the sine function, we could use the tangent inverse of x notation, but that -1 can be confused with reciprocation. So rather than do that, I prefer the arctangent notation. Now, the output of this is, of course, the input rather of the arctangent function is the output of the original tangent. So the slope of the terminal side of the angle. And the arctangent literally translates as what is the arc or angle of the circle whose terminal side has this slope. So again, the arc length and the angle measure in radians are equivalent on the unit circle. So the domain and range then should be fairly simple. We just have to interchange them from what they were for the original tangent function. So if the range of tangent was -infinity to infinity, then the domain of inverse tangent is -infinity to infinity. As for the range of the inverse tangent, we must use the restricted domain, not the original. So the range of the inverse tangent function is -pi over 2 to +pi over 2. So again, tangent is got a nice, simple, easy restriction to find, and the rest of it is just taking what we know of the tangent function and just flip-flopping it, inputs and outputs, to get the arctangent function.